So hello everyone, I'm Chong from Princeton University. Today I'm going to present our PatchCURE paper, a defense framework against adversarial patch attack. My collaborators are Tong, Sihui, Jana, Suman, and Prateek. I will start the talk with the problem setup. First, what is the adversarial patch attack? It is a variant of adversarial example attacks against machine learning model. The attacker has arbitrary control over pixel within a localized image region, a patch region. Then the attacker can optimize the patch content for malicious purpose like misclassification. The interesting thing is that the attacker can print and attach the patch to a physical object. Then images taken from that physical scene can become malicious. The stop sign with an adversarial patch can be misclassified as speed limit. We want to build defenses against this patch attack. One of our defense objectives is to enable certifiable evaluation of robustness. That is, in addition to designing a defense algorithm, we aim to develop a robustness certification procedure. It takes the defense model, image, label, and threat model as input, and it determines if the model is robust or not. If it's robust, we can have a certificate which says the model prediction on this image is always correct, no matter what a white box adaptive attacker within the threat model does. So here, white box adaptive means the attacker can know everything about the defense, including the defense algorithm, parameters, model architecture, and weights. The only requirement is that the attacker should follow the capability defined by the threat model. An example of the threat model can allow an attacker to place a 32 by 32 pixel patch on a 224 image. Then the patch can be placed at any image location and have any malicious content. The certification needs to account for attacks with all this different flexibility and analyze the worst case scenario. Then we will use the certification procedure as an evaluator and apply it to different images from a test data set. We compute certified robust accuracy as the fraction of images with robustness certificate. This accuracy is the provable lower bound on model robustness against this threat model, and it will not be compromised in the future. Research on certifiable robustness against adversarial patches has made significant progress. Here, I use the image data set as an example and plot the clean accuracy and robust accuracy of different defenses and undefended model. We can see the best defense here has a high robust accuracy and also high clean accuracy that is close to undefended model. Looks promising. However, if we replace the clean accuracy evaluation with the inference speed and plot the figure again, we will find these defenses either have poor computation efficiency or poor robustness, and there is a large blank region in the figure. Observing this, our key research question is, how can we build defenses with tunable defense performance to fill this large area? To answer this question, let's first discuss a powerful defense strategy to understand why defenses with high robustness can have poor computation efficiency. It's called pixel masking. The key insight is that since all adversarial pixels are localized, we can use a mask to remove all pixel corruption to neutralize the adversarial effect. A popular strategy is to apply a set of masks to different image location and compute model prediction on different masked images. Then we can analyze the pattern of different masked prediction to identify the correct label recovered when the mask removes the entire patch. These strategies, however, requires multiple expensive end-to-end model prediction on different masked image, and the computation overhead can be 1 to 2 orders magnitude larger than undefended model. So one question here we have is, how can we reduce the computation overhead but without losing our certifiable robustness? Our idea is to perform masking in the feature space instead of the input image. The key insight is that only layers after the masking operation requires multiple passes of computation. If we mask at the input image, we need multiple passes through the entire model. If we mask at some intermediate feature layer, we only need multiple passes on a subset of model layers. And this saves us a lot of computation. Additionally, by adjusting the location where we perform the masking, we can systematically tune the computation efficiency. And here is one more question about this strategy. How about robustness? Is this strategy still robust? Recall that we can perform pixel masking is because we know pixel corruption is localized, so we can use a mask to remove it. Does feature space corruption have the same localized property? No, unfortunately. Let me give you an example. Consider two layers in a vision transformer architecture. The attention operation allows each token or feature to receive signals from every feature in the previous layer. It has a global reset view. When there is an adversary, this large global reset view can hurt robustness. Why? Because one corrupted feature can influence every feature in the next layer and cause global corruption. Since the corruption is no longer localized, we cannot use masks to remove corruption for robustness. So what can we do? Our solution is to enforce small reset view on model layers before the masking operation. Instead of allowing attention across all features, we divide features into small groups and only allow attention within each subgroup. With this design, one corrupted feature can only influence a limited number of features in the next layer. So we still have since we have localized corruption, we can use a mask to remove corrupted feature and use the remaining benign features to recover the correct prediction. Based on all this idea we have discussed, we developed the PatchCURE defense framework. The objective is to convert an undefended vanilla model into a defense model with tunable computation efficiency and certifiable robustness. So here I want to note that for undefended model, they usually have large reset view for a larger model capacity and higher model performance. Now, given the vanilla model, we will first split it at its kth backbone layer. Then we have two submodels. We will convert the first model to have small reset view. We have discussed the strategy for attention-based network. And for convolutional network, we can adjust the kernel sizes and the strides to enforce small reset view. Then the third step, we will insert a secure operation layer between two submodels. One example of the secure operation is the masking-based defense we discussed earlier. These three steps build a PatchCURE defense instance. And to make a prediction on a given input image, we will first use the SRF submodel to extract the feature map. Thanks to the use of small reset view, only part of the feature map can be corrupted. Then because due to this localized corruption, we can use secure operation like masking to remove localized corruption for a robust prediction. And note that this secure operation can reuse the extracted feature map and only involve multiple calls to a smaller LLF submodel. This gives us better defense efficiency. As for robustness certification, we can consider the partially corrupted feature map as an input image to the LLF submodel but with localized corruption. So we can simply apply off-the-shelf certification technique to the LLF submodel to derive robustness certificate. Now let's simplify this diagram a bit. We can show that with this pipeline design, we can adjust the location where we split the model to balance the defense performance. As we split at a deeper layer, we can reuse more computation, have better computation efficiency, but this is at a small cost of certifiable robustness. So how does the trade-off look like? I will use the ImageNet dataset again for evaluation. So here we consider certified robust accuracy and also the inference throughput on a single GPU. This is performance of undefended model, zero robustness, but high throughput, and there are some defenses from the prior works. And here are our PatchCURE defense. From the figure, we can see that the PatchCURE provides a family of defense instances with diverse computation efficiency and robustness, and it's clearly the best across all different efficiency levels. This is useful in practice when we want to build an optimal defense given certain computation budgets. Also, I want to note that if we consider the efficiency to be close to undefended model, our PatchCURE achieved a large robustness improvement, 18% from prior works. And our efficient PatchCURE instance even outperformed many inefficient prior works. So this demonstrates the strength of our PatchCURE design. In addition to the defense performance, I also want to show that PatchCURE is an extensive and powerful defense framework. All defenses that are scalable to higher resolution images like ImageNet can be viewed as an instance of PatchCURE design. But with different SRF submodel design, LRF submodel, and secure operation, and splitting layer. So here I provide a subset of examples here. So this marks the end of the talk, and here are some quick takeaways. So we propose PatchCURE as a defense framework with tunable certifiable robustness and computation efficiency. It is a feature-space defense with a combination of SRF and LRF techniques. So we show that we can achieve fast robustness across all different efficiency levels, and it subsumes many defenses that are scalable to high resolution image. That's it. I am happy to take questions.